Okay, we have a linear distribution of charge on a rod here. We want to find the electric field some distance y from that rod. So I have set up the relevant equations that we need, and I've done a little derivation of lambda here. But where do we start? We need to add up all the electric fields contributed by each individual point charge on this rod to get the total electric field at this point here. So I'm going to write that we have the integral, that's the way to sum things and using calculus. We have the integral of all the electric fields is going to be equal to the integral from the 0th charge to the qth charge. So here we have 0 charge q0, here we have charge qq, say, all the way over. So we need to add up all the charges, and then that's just going to turn into some k, and then we're adding up the charges, so q is going to instead be dq, and then we're still over r squared, and I have the r hat just because both sides are a vector, so you need to stay consistent like that. Now, how do we actually integrate in this space, this charge space, call it? Well, I've got this really nifty lambda. So lambda is going to be q over x. So lambda, the linear charge density. How much charge do I have in this length x? So on the macro scale, I can say I have some charge q, that is some discrete value q, distributed over some discrete value x at an infinitesimally small section of this rod. I have some infinitely small q over some infinitely small x, distance x, and so then that relation stays the same. Now, the tricky part here is to realize that dx, this really small section of the rod, can be expressed as r d theta. So r d theta, if you take some circle here, and I have the center of the circle, and I want to figure out, here is my dx, right? I can consider it an arc length. Because we're at some infinitely small scale, we don't really notice the curvature of the circle. We have some angle theta, and we have the radius, and that will tell us the arc length. The dx is actually equal to, r is just going to continue to be r, so we have r, and this theta. Because we're measuring an infinitely small arc length, our theta has to also be infinitely small. So we have dx, this arc length, is equal to the radius of our circle times the infinitely small angle that describes that arc length. So here we have that result, and that is what I substituted right here. I have dx equals r d theta, so I have dx equals r d theta, just like that. Now we can rearrange this, so we have lambda equals dq over r d theta, rearrange it, and now we have this relationship right here. Very nice. So I'm just going to plug that into my electric field calculation. So we have k, and now we have, instead of dq, we have lambda r d theta over r squared. And then we still have that r hat. Now let's cancel some things out. So we cancel those out. And then also, since lambda and k are constants, they can come outside of the integral. So we'll have k lambda, the integral of d theta over r hat. We were saying that we're integrating from the 0th charge to the qth charge over here. Now that we're in theta space, we need to integrate not from 0 to q, but from minus pi over 2 to pi over 2. So this is just saying that our angle theta, we're considering that this line of charge is infinitely long, at least from the perspective of this point. Remember the assumption, we're sufficiently close to this rod so that the rod looks infinite, and so we could say that as theta approaches 90 degrees or negative pi over 2, that is the boundary over which we are integrating. So negative pi over 2 to 0 comes right here, and then 0 to pi over 2 goes all the way out over there horizontally. We still have this r here. R is going to depend on theta, so we need to find some relationship to represent r in a different way. Y is equal to r cosine of theta. R is actually y over cosine theta. Plug that into our little equation here. We have k lambda integral from minus pi over 2 to pi over 2 d theta over y cosine theta. The contributions from the left side of the rod are going to be equal to the contributions from the right side of the rod. So instead of integrating over the entire rod, I'm just going to integrate over half of the rod and multiply by 2. So I'm going to say, instead of from minus pi over 2 to pi over 2, I'm just going to say from 0 to pi over 2. So we have 2k lambda cosine theta d theta over y. Still have that r hat there. The integral of the cosine is just going to be the sine, and then the sine from pi over 2 to 0. We'll write that down in a second. So we have lambda, and then we have the evaluation. Sine of pi over 2. Sine of pi over 2 is 1. Sine of 0 is 0. So 1 minus 0 over y, and then times that r hat. 2k lambda over y r hat. That is equal to the total electric field at this point here. I just want to reiterate that this little explanation here is completely for your enrichment. Do not get worried about the math. The math does not matter too much. I will point out that the only physics that's going on here is, or the representing mathematically part of our problem solving steps, it comes right here. We've represented the electric field, we've written down our relevant equations, and now how do we represent the situation mathematically? We say we want to sum up all the electric fields to get some total electric field. And so that's what we did right here, and that's pretty much all the physics that you need to do, is like understanding the physical situation that we have. So once you've done that, it just comes down to solving, and solving sometimes can be trivial. Sometimes solving is not very trivial. Regardless, we still end up with some result, and if we evaluate it, we'll just say that it looks nice. It works out. The interesting part of this result here is that we find that the electric field in a linear charge distribution does not depend inversely on the distance squared. It depends inversely on just the distance. So we get rid of a factor, an entire factor of some of the distance. So it's pretty interesting. I want you to think about what would happen if instead of a linear distribution of charge, we had an area distribution of charge. Would we find that our relation changes? Maybe, maybe not. So here's the result. Have fun.